Next, we're doing the second part of Lab M6 for the garage door opener. Personally, I really like the garage door opener project because everybody understands a garage door opener. No one has to sit and think real hard about the process. The garage door goes up, it goes down. Everyone has seen an electrically driven garage door. In the first part, we did the traditional start-stop circuit with seal-in logic. In this part, we're going to go a little bit further, where we have two start-stops, one for going up and one for going down, and then some interlocking between them. So let's get right at this. This is where we left our project. We had a standard stop-start circuit. And this stop push button in the field wiring is a normally closed push button, which means when the button's not pressed, the contacts have continuity and they put a high voltage on the screw terminal of the input module, so this instruction would be true. This is a normally open push button, which means if it's not pressed, the screw terminal for input 0 is at a low or 0. This is a, if you like, a relay or a motor starter that will run the motor in the up direction, pull the garage door in the up direction. Of course, this is a seal-in contact from this device. This output is controlling that electromagnetic switch that switches it to the up position, but this is not an actual contact. This is a true if on. So if we turn this bit on, this will be true. That bypasses the up push button. Do you think that this should be wired fail-safe, fails into a safe state? Yes. How would you do that? The switch opens when reaching the limit of up or down. So in other words, we would be using a normally closed, and then when it hits the limit, it opens. Now, if you're not familiar with what a limit switch looks like, I'll just pull one into view here for you real quick. And you notice that this has two positions. It probably has a Form C contact. The arm is adjustable, both in how far it extends and the angle. So you can loosen the adjustments and place this. See, this is a spline shaft. So you can loosen up this bolt right here, slide it off, and then rotate it around to the position that you want, and then you can extend the arm up and down. So that's a limit switch. So we're going to need to add a limit switch that stops the motor from continuing to power in the up direction when it hits the limit. If you don't, then you're going to run into a hard stop, put a lot of stress on the chain, the gears, and probably overload the motor and trip the breaker. So I had you add in a true if on, and then we had you assign that to input 5. Over here you can see that input 5 is the up limit switch. If we just type in IN, you can drop down and double click on IN05, and there we have it. So when the garage door is going in the up direction, when it trips the up limit switch, that instruction is going to go false. Output 0 will go to 0, and that screw terminal goes out to the coil on a starter or a contactor, and it goes from being on to de-energized, and the motor stops running in that direction. I think that's pretty simple. In the book, why are we using a true if on input 05 and not a true if off? Because we want it closed when it's untripped to enable it to go in that direction. And if it's in place, if the switch has actually arrived at the limit, we want it to open. An untripped switch places the input 05 in the on condition, saying that it's not tripped. Remember, this is fail-safe. Save, download your edited project. So first we save it, then we download it. Okay, here we are, downloaded online, and we have our I/O with its aliases, so we can see the logical value and in some cases maybe the physical value. First question is, why do we want input 0 in the on condition? We want it in the on condition because that represents the state of the bit in memory when the screw terminal has a high from the field device, meaning that the switch is closed because it's not tripped. Okay, it's not pushed. This is a momentary push button. And when we push that button, that's going to go false because we want to break logical continuity. Now, in order to go up, we also need input 5 on. Now, if you push the up push button, you have logical continuity. That sets the bit in memory, OUT00 to on or 1, and then during the IO update, the output image update, it's going to take the state of those bits and send them out to the screw terminals through the opto-isolators on the controller. So input 00 represents a stop push button not pressed. Just by looking at the state of the memory locations as they affect the true-false state of instructions, is the garage door currently up, down, or somewhere in between? Because the up limit switch instruction, input 05, is true, meaning that that bit is on, means that the up limit switch is not tripped. Always keep this in mind. The limit switches are using the normally closed contact. So if you were up, the contact would be broken, the screw terminal would be 0, and the bit memory would be off, and this would be false. This is true because the garage door is not up on the limit. Notice if in the manual I have the stop push button I have it over here on this side. Now this is the standard way to draw a start-stop circuit. So at some point I flipped it around. The stop push button could be over here. Okay, I flipped it around. I moved the stop push button, the instruction, from this side, this end of the rung, over to here. This is the little blue piece of line I wanted you to notice. The instruction is true. This instruction is true. But that little piece right there says to this instruction that the rung is false. So these two are displayed red for our benefit to see what's true and what's not true. So anything that represents the rung, which is going to be this little short piece right here, that little piece right here, and this longer line, represents the state of the rung. So even though these instructions would be true if the preceding part of the rung was true, the rung is still false, and that's your clue right there. Now you can see that neither one of these are true, even though both of these are true. So one of these two would have to go true in order to turn on that motor and run it in the up direction. A question in the manual was, where is the garage door right now? If the up limit switch is not tripped, because remember, if this was tripped, this would be false and you couldn't run the motor up, because it's already up. Because this is true, that means it's not up. So that's the only conclusion you can draw. So it could be all the way down, or it could be 1/8 of an inch off of the limit switch, input 05. So look at this, the only thing you know is it's not up. We also ask you to look over here in your variable database, and it asks, is there any indication here that would declare the position of the door? Yes, it's not up. That's on, so it's not up. You have nothing else here. That's the only indication that you have, is that it's not up. If the limit switch is on, normally closed, and the down limit switch is off, normally closed but held open, what position is the garage door in right now? Down. Now we don't have the down limit switch in our logic yet, but the question still begs the answer, it's down. Momentarily turn on input 01, then off. So basically what we're doing is we're going to toggle this. I'm going to go down here and double click, and you see it go true just for a split second. And during the first scan, which remember, that's a fraction of a thousandth of a second. It's in microseconds. This is true because that's true and that's true. It turns on bit 0, and that makes this true. So when you come back in the next scan, or many scans later when you let go of the button, this may be false, but because this is true, you still have a logical continuity to keep output 00 in the on state. What is the garage door doing right now, this instant, judging by the state of the logic? Well, the motor up is on, and that means it's going up. How long will it continue to do this, to do what it's doing? How long will it continue to go up? Until input 5 is tripped, until the limit switch is tripped. Okay, so now we've hit the limit switch. This instruction goes false, and the motor turns off. So the motor turned off, says what happened? Motor turned off. Why? Because the door hit the limit switch and tripped it and removed logical continuity in this rung and dropped out output 00. In what position is the garage door right now? Well, if this is false, then that means it's tripped, which means it's in the up limit position. Can the garage door continue anywhere with just this logic to control it? Absolutely not. Once you trip this limit switch, you would have to go up in your garage ceiling with a wrench or screwdriver and remove the arm on the limit switch to allow it to continue going up. Of course, you don't want to do that. But the answer is no. Why cannot the motor be energized again with this logic? Because the limit switch is tripped. What must happen to allow this wrong to be true again? Door moves down and off of the limit switch. Okay, disconnect and go offline with your program. I'll save. Then I had you move the instruction over here so it looks more conventional. So we had you move the instructions, and then we had you copy and paste this wrong. So I go to the head of the wrong, so the focus is here, and I do Control C, Control V. That gives me a copy. Now, I had you save this, download, and go online and execute it to demonstrate these two rungs can operate even though you have two OTEs, direct coils, addressing output 00. Because the logic is identical, there's no conflict. Now, if one rung had different conditions than the other, then last man wins. Rung 2 would dominate. As a matter of fact, if you could watch the conversation between the logic and the memory locations, you would see that rung 2 was the last one that spoke to output 00 before the end of the program scan and the output image update began. So we're going to skip actually downloading this and going online with it to demonstrate that there is no conflict. Rungs ran without any interference. And the questions in the book: does this logic result in the identical condition as it did when there was only one rung instead of two identical rungs? Yes. Why? There's no conflict. Which one of these rungs is relevant based on your knowledge of how the program is scanned and executed? Last man wins. Rung number 2 was the last logical address to output 00. And we had you save and disconnect, which puts you right where you're at right now. Then I had you edit this rung for the motor down direction. So we can go here, pick input 2, which is down, and then we can go here and pick input 4, which is the down limit switch, and then we can go here and pick output 1, which is motor down. So now we have a down push button, a down limit switch, and a motor down coil. Now remember, these can be two coils, or rather these two outputs can be controlling the two coils of a reversing starter for a three-phase motor. Because we're really doing an industrial garage door open here, not like one in your garage. The mechanical is all the same, and it's got limit switches. The only difference is using 3 buttons or 1 button. I personally prefer the 3 button. So we've edited this rung. Now we're going to save, download this logic, to save and download. The first thing I would say about this image is the door can't go up or down. Considering that input 4 and input 5 are mechanical switches that are being held open or springs holding them closed, there's no way from this screen that you can make that motor go up or down. You can't even toggle output 0 or output 1 and keep it on because there's no logical continuity. Just like if this were a relay circuit, there would be no electrical continuity, which means that the garage door cannot possibly be in this state unless one of those switches is broken, one or both. So we have to turn on input 4 or input 5 to declare that it's either up or down. Now remember, if you get turned around in your thinking, if you want it to be in the down position, then you turn on this switch so it can go up, or it can't go down. So let's turn on input 5. Now it can go up, but it can't go down. So that means that it's down right now. For this to be false, that means this down limit switch is tripped. Open in the screw terminal is 0 volts. The bit memory is off. True if on is false. Okay, so we are in the down position. And the question asks, what position is the door in the above screen capture? And this is what the screen capture did not look like. So let me switch it. So this is the image in the book. They got input 4. I should say I wrote this manual. This is all my work. So if that switch is on, you can go down, but you can't go up, which means that it's in the up position. Can both limit switches be tripped, made simultaneously? No, that's how we started out. Remember, we had both of the limit switches tripped. So false is tripped in that position. Why can't they both be tripped simultaneously because of the limit switch positions. The limit switches are positioned so they are tripped at the opposite ends of the movement of the door. I mean, these sound like no-brainer questions, but what we're doing is we're nailing down and making sure everybody has thought about these things. Can input 4 and 5 both be equal to 1 or on simultaneously? Yes, they could. I can turn on input 5. That means we can go up or down. Well, obviously, if the door is not up and it's not down, it's somewhere in between. That's what this represents, somewhere in between. Toggle input 2 on off. So input 2 is the down push button. So when I say toggle it, I mean go to input 2 and double click on it. You turn it on and right back off. Oh, I see something I didn't change. I suppose this is good. See here, when I edited this rung, I forgot to edit this. Now this is real common to miss an edit when you're copying and pasting rungs. Let's say you have 5 rungs and it's all basically the same logic, but it's for different outputs with different conditions. I make this mistake at least once or twice on every project. So I'm going to change this and come right back. Okay, I flipped, or rather I edited this to be the seal-in contact for this output state. Now I'm going to go to input 2, click it twice. You can see the motor's down, running down. The motor's running down. What is the garage door doing based on the state of output 0? It's going down. One input changes state within seconds of the door moving off of the travel limit. If we are going down, then the up limit switch went on. Now if we were all the way up, we started halfway in between. So let me go back. We haven't done the stop push button yet, so I'll double click that. Okay, it stopped, right? So let's say that we were up, which means that input 4 would be on and input 5 would be off. Input 5 is, we are in the up position because this is false. So right now the only place we can go is down because the limit switch is up. This is tripped, false, therefore it's all the way up. We start it down, double click on 2, and then the first thing that's going to happen is that this is now going to change state. Even though we're going down, the door came off of the up limit switch and this went true. So if I stop it, double click on 0, now both of those are on, or true, which means it's not up and it's not down. So from that point we can go down or up, and that's why I like the 3-button system better than the 1 button, is because if the door is stopped, I don't have to wonder which direction it's going to go, especially if I'm not familiar with the door. It's not my door, but I want it to go down, not up, rather than hitting a single button. Oh, there it goes up, stop, hit the button again, then hit it again, and it goes down. So that's why I like the 3-button system the best, because it's more deterministic. Okay, we had you toggle input 5 off. That would indicate that it's up, right? And then we had a question in step 21 or so on page roughly 126 in the screen capture on the right, and it looks like this. What is the garage door doing based on the states of output 0 and output 1? Not moving, not up or down. Where is the garage door right now? In between up and down. Using this imagery right here, looking at this logic and the state of these conditions, which direction can we send it? Up, down, or either? We can send it either up or down. Based on the current state of our memory locations in the logic, in what state are the limit switches, open or closed? They are both closed. Input 4, input 5 are closed. The bits in memory locations, dominated by the position of these switches, are they on or off? They're on. Now another thing I had you do, and I'll go ahead and do this. I'm going to go offline, change these to the opposite instruction, true if off, without changing input 4 or input 5. So right now, neither limit switch is tripped. Okay, we're not going to change the wiring on the limit switches. We're just going to change the logic just to demonstrate something. So we'll save and disconnect. Now, when I do this, I just drag down instructions next to the ones I want to replace. That way I have the address right in front of me. See, right there, input 5. Now this is so simple that you could remember input 4 and input 5. So now we want to delete the old instructions, so we select there, hit delete, Select here, hit delete. Now we're going to save and download. Okay, we're back online now, and notice we didn't change the state of the field devices. Okay, so now you can see the logic's never going to work. You're never going to be able to run it up or down. For us to make this work using a true if off, we would have to rewire the limit switches using the normally opens instead of the normally closed. In other words, and we'll look at these right here. Okay, these are both on. So let's turn these both off. Well, now you can go up or down. But notice that neither 4 nor 5 are on. The screw terminals are low, which means that those limit switches are both open. So if you run the motor in one direction, it's going to trip one, turn it on. So let's just do that. We'll run it in the up direction. Now we're going to hit limit switch 5. Okay, 5 is on, but see, this is false, and that's fine. The difference between using the normally open and normally closed is to fail to a safe condition. So let's say that we were running this up. Okay, it's running up right now. And let's say that a forklift came by somehow, or somebody operating something at the loading dock broke the limit switch 5. In other words, limit switch 5 is not going to change states when the door hits that limit switch. Bad news. If the wire breaks, there's no difference between that state right there and a wire broken because it's off. So now we're going to, we saved, downloaded it so you could operate it as seen. Can both, looking at this current logic, can both limit switches be in this state simultaneously? Yes, this state right here, not the one in the book. In the book it was 4 and 5. And the question was, can both limit switches be in that state? No, not unless one of them's broken. Are they both tripped? According to that, they're both tripped, but that's not possible unless there's a mechanical malfunction. Are they both on or off? They're both off. Can you determine what contacts are used on the limit switches by looking at the logic? In other words, if you look at this logic and you know how the garage door is supposed to work, could you discern what contacts the designer, mechanical, electrical designer, probably used for this circuit? Now you can say yes or no. You can say yes, that they're probably using normally opens. Or you could say, well, I don't know, maybe one of them's broken, and that's why they both look like they're tripped. Can you operate the door in either direction based on what you see in this image? No. No continuity to either direction. Whose responsibility is it to flip these switches as you're testing this simulation? In other words, we don't actually have limit switches being hit by the garage door. So as you test your logic here, who's responsible to make sure when you go up, you untrip the down, and when you get up, you trip the up, and when you go down, you untrip the up, and then when it gets down, you trip the down. You're with me on that. With memory locations input 0 and 4 on, as shown in the previous screen capture, with memory locations input 0 and input 4 on, as shown in the previous screen capture, which is the only direction that you can motor the door up. Which true if off instruction is true? Input 5. Which limit switch is tripped? Down, input 4. And that was pretty much the end of the lab project. I just told you to exercise your logic. Now, I would change it back because you're going to do so in the next lab. You're going to need it changed back. So I'm going to go offline and change it back. And here we are back with our conventional logic. What can you do with this system right now? You can run the door up until it hits the limit switch. You can run it down until it hits the limit switch. And you can stop it anywhere in between. And you can start it up from anywhere in between in either direction. But if it's up, you can only go down. If it's down, you can only go up. And remember that to get the full picture of what's going on here, you would need to get the electrical print or the documentation so you can see that what's hooked to this screw terminal and this screw terminal are normally closed contacts, the same thing with the stop push button, and that these are normally open momentary contacts. We're just assuming that looking at this logic, and we're operating it based on that assumption. Okay, that gives us some basic control to go up and go down. We have two rungs of logic. Sealing logic, hit the up button and it goes up until it what? Engages the limit switch, which is wired, normally closed, which means when it trips the up limit switch, it opens the switch. And once that switch is open, it can't go up anymore. You cannot restart that rung to go up until you back off of that limit switch, and the only way you can back off the limit switch is to go down. So you can hit the down button and it will run down until it hits the down limit switch. Now you can stop it anywhere in there and then make it go in either direction. So if it's sitting in the middle, not up and not down, you can go up or down. Well, we're not done with this yet. I mean, you could control the garage door with that simple bit of logic, but that's not really good enough. So let's conclude this lab, and we'll see you for the next one.